Okay, good morning, everybody. October 21st, back with Dr. Mike Ellis from College of Business at UCA. And take it away, Mike.
Okay. Thanks, Don. Good to be back. I know you guys are kind of wrapping things up. It's my understanding that you've talked about some R stuff, and I saw on your Blackboard page there the stuff that Dr. Worley brought in from the math department a while back. And I've also looked at the PDF that she gave you, which was an outstanding introduction to R stuff. I'm going to today talk about some machine learning / data mining stuff. And I've been going back and forth about exactly what I should do. And I'll tell you the way that the thought that kind of managed the whole process for me is one of my favorite quotes that are used whenever we talk about learning a new computer tool. Of course, it goes to any kind of a tool, is that a fool with a tool is still a fool. So if I just give you a bunch of R stuff, I don't want to leave you with just having a tool in your hand. And so we're going to talk a little bit about some background. So in the files that I sent you, there's a lot of stuff in there, and some of it is just for your reference, but I'm going to go through some background material quickly and then get to the code. And we might be going back and forth to explain some of the stuff. The first example code, decision trees, we're going to do a lot of typing, not real extensive. And then the other two, a little less typing because there's some longer statements and things, but we'll get into cleaning up some data and some other stuff. You might also notice that some of the things, we might do something earlier that we could have done later, but we don't. And it's because these are all jumbled up from the way I do the class. The other thing is that I'm distilling what I hope is going to be about 3 hours worth of stuff from a semester long class. So it's real hard to figure out where to cut and where not to cut. So trying to give you a taste of what's out there and some of the R stuff that we use for it, and go from there. I don't remember if I mentioned last time, but what I've heard in a lot of cases is that a lot of people in the field, not necessarily in Central Arkansas, but a lot of other places, because it's different places, they'll use Python for cleaning and preparing data, and they'll use R for actually modeling. Now, lots of places use one or the other or something else for the whole process, but that's kind of where it comes in, and why we're giving everybody a taste of both of them around here. So let me go in here, and like I said, I want to kind of give you a taste of this. You'll see, if you see in the lower left-hand corner of my screen, I have 71 slides here. Like I said, we're not going to spend a lot of time on each one. It reminds me, we had somebody that came and interviewed for a job here and was going to give a 40-minute talk on his research, and he had 92 slides. And we still talk about him now several years later. So I don't want to leave that kind of a taste in your mouth, but I do want to talk about some of the basics before we go to the code. And like I said, a lot of this is for your reference. Before I forget, in that, in fact, maybe I ought to just change my screen sharing to go to that. In that document subfolder of what I sent, there's a PDF of these slides, 2 slides to a page. And then this R4 Beginners V3 PDF is an excellent beginner R intro to it. It's from Computer World. It's a few years old, but the basics are the same. And it's the one I give my students, and it's just got all of the high points. So you're not going to get any serious modeling or anything in there, but it's a real good basic introduction. So that's a reference there for you. Both of those there, these slides, and then that PDF. And like I said, Dr. Worley stuff is pretty comprehensive too. So this is the book that I use, Machine Learning with R, from Pact. Pact is an interesting publisher. They have some deals where a few dollars a month get you unlimited access to all of their texts. They're all written by practitioner types. This has been I really like this book. I looked at it, one thing to try to keep the cost down. but it also has a lot of practical stuff in it. So um, whatever that's worth, that's what we use, and I really like that book. Some of these examples we're going to do today come out of that or have been modified from that. So like I said, I'm not going to spend a lot of time on this, but we're going to do a little machine learning, 3 different techniques later. And I just want you to be aware of some of the stuff that we're doing. Keep in mind, and this is going to be a big thing if you're actually using some machine learning, is that the model can only cover what is in the training data. So you can't model anything that's not represented in the training data. It doesn't extrapolate. It doesn't use any common sense. You get all those recommendation engines that say you might like this. Well, you might have already bought it, but unless it's connected to a database and stuff, it doesn't know. So it doesn't have that kind of stuff to be able to figure things out on its own. We talk about artificial intelligence, but it's not really intelligent, not yet anyway. So we see a lot of stuff with handwriting and text recognition where it's close, but not quite. But it's getting better. So data mining, I kind of think of data mining as applied machine learning because there's lots of stuff in both fields that doesn't really cross over. Like the example there of analyzing traffic patterns for future road design versus self-driving cars. You can use machine learning in order to do the analysis, but it really doesn't apply it to anything. And the data mining goes a little bit further. So usually a bigger scale and having to do things quickly. So the reason for doing this is to find meaningful patterns in the data. And we're going to do some of that. One thing is that I want to emphasize is, and I have to do this with students all the time, is remember that a model is the representation of the relationships. It's artificial, it's not reality, it's an approximation. And we're going to talk about that a little bit more too. So there's some stuff here that are not data mining, but we still talk about them a little bit because descriptive stats and exploratory visualization are early phases. And we kind of did some of that with Python, and you've been working on stuff along those lines. We're not really going to do any of that today, but they're the beginning part, getting to know what your data looks like. So actually, let me, the abstraction phase is to try to take things from that data and abstract it into a model that we can hopefully generalize. So we look at the different candidate models and try to pick the quote best one to do what we want to do. Now, what's the best one? That depends on a lot of things going on in our the design of our analysis. So just like we talked last time about some data things that have to be decided up front, that's usually what we have to decide up front too. We're going to come back and touch on some of these too as they go in. Here's another one of my favorite quotes that we use all the time in this arena. All models are wrong, but some are useful. The idea that you cannot have a model that is going to have 100% performance simply because there's lots of noise and other factors that you can't get in there. There's plenty of research, behavioral research that we work on in the College of Business where if we can describe 40% of what's going on, that would be like game-changing stuff. So in physical sciences, you can explain a lot more, but when you get to behavioral, not so much. So we're also run into a problem called overfitting that we'll talk about too. We're going to use training data. That's what we use to create the data, and then test data to see how the model works. So the training data used to create the model, test data to see how it works. So it's data that we know the result for, but the model hasn't seen it, as we say. It hasn't been run through the model. So I mentioned noise. There's the 100, accuracy and overfitting. We can't just keep going after more and more efficient models. And we can overfit or underfit. And I'll show you a couple of examples. Here's an underfit model. You see all those points there, and that a straight line through there. It's like, yeah, you can get an equation for that, but that's not really that great. Or you can just connect all the dots and get an overfit model, but neither one of them works very well. If you find a good fit, now you can find a model that's useful. So keep that in mind as we're going forward and looking at some of the code. And then the other two biggest things that we want to talk about here is that there's two types of categories, supervised and unsupervised. They're actually pretty straightforward. With supervised, we're trying to predict a specific target, something we know in advance. What is the adoption rate expected with this marketing campaign? How many people are going to buy this item? How many people might die of COVID in the next 6 months? I mean, we're looking for a pre-specified target variable, and unsupervised is we have no target variable. So we're going to do three techniques, and we're going to use both supervised and unsupervised in them today just to get a little taste of that. So a little bit more about those. And then I think the last thing that I wanted to talk about before we get into actual methods is that we really need some kind of a process in order to manage this whole system and give us some guidance. So the CRISP DM is really the leading way of doing that. There's a couple other models, but CRISP DM is far and away the methodology that more people use. So that's what I tend to use to organize it. Here's one of, I don't know, dozens of graphics that you might see on it. But all it really is a problem-solving process. So first, the business understanding. Why are we doing this analysis? What's it going to do for us? It's essentially understanding the problem. And then what data do we have? Where did it come from? And then cleaning the data, getting it ready to go. Now that can be 80% of your total project time. And then building a model, testing and evaluating, and then deploying it out there. So there's nothing earth-shattering about this process. It's just a matter of going through. And then as the previous graphic shows, sometimes you can learn something that you have to go back and make a change. Of course, if you're just given a bunch of data and you've got to do something with it, you can't necessarily go back and collect more data or change the way it is. You're kind of stuck with it. So, but if you're going to do an overall project, then you can use something like this to kind of guide your design. Is data mining a science or an art or a little bit of both? I think it's a little bit of both, because you've got to have some experience to make some decisions. I always tell my students, you're not going to be asked as a new graduate to go out in your first week to create a neural net model. It's even people that have been doing it for years don't always understand exactly what's going on with a neural net. So it does take some experience to get good at it, and but you do need to be familiar with some of the stuff. Also want to take a quick mention of ethics. It kind of goes into some of the limitations I've talked about. Just because you can do something doesn't mean you should do it. There's a really good example of targeting maternity customers a few years ago. I love having a discussion about it, but we don't really have time set aside for that today. But should they have done it? I don't know. They got a lot of backsplash on that, but most people have forgotten about it now. So I guess it's not that big of a deal. This book, Weapons of Math Destruction, if you're at all interested in these kinds of things, this goes back. One of the main themes of this book is that a model is constrained by its training data. So if you have training data that is biased, then your model is going to be biased. And Kathy O'Neill talks about credit scores and a lot of other models in here that are biased against different groups because the data that goes into them are biased, and you have to be aware of that. So it's not a real long read. It's pretty interesting. She used to work for some companies doing big data analytics type stuff, and now she's a writer and does some other consulting and stuff. So we're going to talk about, like I said, supervised learning. We're going to do decision tree example, and then a k nearest neighbors classification example. And then we're going to do unsupervised learning with k-means clustering. So we'll talk about what's involved there. Now, I've got some stuff in here about the different methods. Decision trees, I think, are pretty straightforward. They're used a lot because they're easy to understand. So we talk about the root node, which is at the top, ironically. Whenever we do representation, and you'll see that in some of the output. And we have the interior nodes and leaves and all those different parts of it. So it's just an algorithm that's represented graphically. That's why they're used commonly, because they're easy to understand. We're only going to talk about classification trees. You can also have regression trees that predict a value at the end. They're just a little bit different. There's lots of different algorithms to use. C 5.0 is the standard, and that's what we're going to use. But one of the other ones you might see pretty regularly is CART. That was the standard for quite a while. But there's a lot of different algorithms, and they make their decisions a little bit different way. So let me give you about 2 minutes on decision trees here. I know I'm rushing. I'm trying to get to the code, but I want you to get a little bit of background. So the idea with a decision tree is that we divide the training set at some sort of, at one of the characteristics to get the best division that we can, and then we divide each of those subsets, and we continue down recursively until we get the purest, quote unquote, subgroups that we can. So we get the items that are most like each other at the end in those leaves. So that's what we're shooting for in the decision tree. Strengths and weaknesses, they're easy to do, but they also have some limitations. We have splitting attributes. That's where we do the splitting, and the leaf is at the end. So another term that you might hear are that these algorithms are greedy algorithms. All that means is that they go with the best option that they have right now. So, lots of times you might look at a decision and say, you know what, this first decision is not so good, but it sets me up for a second decision that's better if I go that path. The decision tree can't do that. There are other techniques that can, but it does miss a situation like that. So I'm not going to run through the attribute. I'm not going to talk about entropy. We do run into a problem with overfitting where it won't generalize. That if overfitting means that the tree, the model, and it's not just decision trees, but it fits the data so well it doesn't work with other data. It's horrible with other data. So we have to be careful about that. We can also go underfitting, and then pruning the decision tree. We can pre-prune, but then we might miss something. So we post-prune, which is what we're going to do. What the model does is it runs the model out as far as it can, the tree, and then it starts cutting back. It's built into the algorithm, cuts back the branches that really don't add much to the model. We're going to use this random sampling visual. We'll talk more about that. Here's some just general stuff on the algorithm, and then we can make the mistakes. We'll come back and talk about that. And then so let me go to the R code. Let me see, where did I lost my, there we go, there's the share. So oh, let me get into decision trees. So let me talk about a couple things about RStudio. I don't know how much time you've spent in it. I'm using a dark theme, which if you go to tools, global options, then you've got lots and lots of options you can change here. And I'm in appearance. So I forget what, Merbivore Soft is the one that I like. I've been messing around with some. The purple comments are a little bit much, but that's the best one I've found so far, for me anyway. You can change the font and the size and all that stuff. Lots of things that you can change in here. You can change stuff with code. You can change tabs and displays and other stuff. I also, the way that I have my view set up is a little bit different. You can change that through global options. You can also change it through view panes here. And I have console on right. You can change console on left is the default, I think. And then you can actually go in here and specify the different panes and things that you look at. So why do I have mine set up this way? Because that's how I learned to use R. So I'm not comfortable with it the other way. I'm just used to the upper left-hand corner has the file where that's where I'm going to type stuff. So this is the console, and you might have used that last time. And you can type in here as a live session all the commands that you want. But I'm opening up over here these files, the R code files, and going in here and saving that. Then we'll see some stuff in the environment. Down here in the right, files, plots, packages. Our plots will be down there, packages and stuff, and help. And I don't need that too much right now. So one of the nice things is that we can independently change the size of all these different windows. So the first thing that I do is run this command, set WD, which is set working directory. And because one of the things with RStudio and with running things from a script file is that you can run lines independent. So I can actually go down and try to run one of these other lines that I have in here, except that they're not going to work because the data is not there. But I can run get WD, and you see my default directory here is in my user documents folder. So I can just set WD and then check, and you'll see it's set. So this is the folder that I want to be in. My paths that I'm writing to get to data files and stuff are based on me being in that location. So you can put whatever the path is in quotes and set WD, and you should be good to be able to do that. So as I said before, that crisp DM gives us an outline of a process of how to run our analysis. And you can see in this decision tree folder, we're going to do some typing. So a little less than the other ones, just because this one's pretty simple and straightforward, quite frankly. So, but the first step in the crisp DM is the business understanding, and you really need to consider that before you start your analysis. When we're actually in the software, it's a little bit late for that. So one of the things in data understanding is you should understand a bunch about that beforehand too, but we can find out about our data. So we're going to load, and R uses data frames. I think you talked about that before. That's another place where the data frames. And then the assignment operator in R is that less than and the dash. You can put that in as a shortcut using Alt and the minus sign. Lots of times, yeah, you can, in this case, I can use the minus that's up next to the 0 on the top of my keyboard, or I can use the one on my num keypad on the far right. My keyboard at home, I can't use the one on the num keypad, so whatever that's worth. Technically, you can use an equal sign there too, but don't do that. Don't even consider doing that. It'll work in most cases, but it won't work in all cases. And any R purists will not like that. So it's obvious when you use this, when you see code that it's R. So that actually helps. So we have read.csv we're going to use. And with RStudio, if we just type, suggestions will come up. We don't have to hit tab like we did in the notebook. So read.csv is the first one there, and we're going to use that. That's just built into to R, and we just have parentheses and then the file that we want. So in this case, I'm going to use whatever path that you have. In my case, I have to go up a level, down to the data subdirectory, and then the credit.csv file. And then I'm going to add one more thing here, one more argument here. And you see, one of the nice things I like about RStudio is it gives you this cheater code most of the time till you make it go away. But one of the things is the way that the data is in this credit CSV is I want to, the best way would be to take a quick look at it, but it has a lot of stuff in there about what different characteristics of the loans and people that might want to borrow money. And we want those things to be the factor data type, which is categorical data. So in pandas, we would change it to be a category. In R, it's a factor. And we use an argument here called strings as factors. And you see there it is. And I can hit tab and accept that. And I just want to make that true. And now when I do that, and I'm going to run, and we can run using the run button up here, or we can use Control Enter, just like in the notebook, which is what I tend to use most of the time. And we get over in the console, it runs the line, and we come back to the prompt. When we have the greater than sign, we know that it's finished. So one of the first things I want to do then is look at the structure. Unfortunately, str, it's not string, it's structure. What does that credit file look like? So let me go back the other way on the windows here. You can also use, like with a browser, you can use Control plus and minus to make everything bigger or smaller. So I'm trying to balance keeping things big enough to see with getting stuff on the screen. So yeah, that'll work right there. So you see this first checking balance, we have a factor with 4 levels because the values are these strings, like here, the less than sign 0 DM. This is German data pre-Eurozone, so it's Deutschmarks. And then we have greater than 200, and there's a couple others. Now, they're actually coded behind the scenes as 1 through 4, but it keeps track of it as this factor variable as this text. We also see we have 1,000 observations, 17 variables. The month loan is integer. We have these factors. I think we have just integers and factors in here, yeah. So we have some, let's see, what was I? Age and all this, housing, it's job, dependence, phone and default. Default is the key one. That's what we're going to wind up predicting. Did they default on a loan? Yes or no? So you see it's 1s and 2s in the data, but it's actually kept in that data type as with the values yes and no. So let me go back. If we hadn't used that strings as factors equals true in there, they would have just come in as strings, and we wouldn't get that extra functionality. So that's what we wanted to take a look at. So the characteristics of the applicant, like what their checking balance is one of them. So let me make that just a little bit bigger. Let's look at that. This table function will look at that, and remember that we use the name of the data frame and a $sign, and then the name of the column that we're interested in order to access it. So we're looking at this checking balance column in credit and just showing a table of values, because we can do table because it's a factor. So it tells us we have the lowest one is 274, and then the next one is 269, and then the biggest one is 63, and then unknown is 394. So we probably need to do something about that. Let's do another table. Let's look at credit $sign savings balance. And there too, we get the suggestion. And then I run that, and you see we get the same kind of thing with some unknown. Now, the bigger this window is, the neater that'll be. And I can always just go back and rerun that table command, and it'll rerun the table. So that's one of the things that is not that good is in some cases, like it did with up here where I was showing the data. As I stretched this, it rearranged everything. But with some of the output, once you do it, it's just stuck. You have to rerun it again. So just a little bit of an annoyance is all. So what about the characteristics of the loan itself, like the month's loan duration? You see, we can get a summary of that because it's a numeric. I'm going to run that again. Let me stretch that out and run that again. So we can get some basic statistics on that. Let's look at another one. Let's look at the credit amount. So let's get summary of credit $sign amount. And so it gives you an idea of what's going on in those individual columns. And then the class variable, the classification variable, or the label that's used, it's a lot of times it's used in this kind of modeling. It's called the label. It's what we're trying to predict. So we can take a look at what is that. Let's do a table of credit $ default. And so we'll see, like I said, this is, did this customer default on their loan? 700 of them, no. 300 of them, yes. So we've got a blend of those. So this data set is 1,000 customers, 700 that didn't default, 300 that did, and then all the characteristics, all these different variables that show what their checking balance and the purpose of their loan was, how long they've worked, their age, housing, all that stuff. So we're going to use all of that in order to try to predict if a future customer might default if they have similar characteristics. Is everybody good to this point? I got kind of amped doing the stuff in the PowerPoint. I'm trying to calm down just a little bit here and
So
make
far,
sure
so good.
Yeah, okay.
Hey, Mike, I missed the hotkey. I've been clicking on run to run each line.
It's Control Enter.
Control Enter run. Okay, cool.
Yeah, and you can be like here, I'm going to click in the middle of that credit. You can be anywhere in that line and hit Control Enter, and it runs that line. Just don't highlight it. If you accidentally highlight a couple of letters, it'll come up and say, hey, that's no good.
Gotcha.
But at least it doesn't blow up on you or anything.
Control Enter.
What does it mean by class variable?
The class, it's the label, it's what we're trying to predict. The classification variable.
Okay.
That's what we're trying to classify. Will possible future customers default, yes or no? So there's a couple of data prep things that we want to do here. And one thing is that all we have are 1,000 rows of data. And so we need to use some of them as training data and some as test data. And we want to get a representative sample between the two. So we're going to use that sample function that I blew through on the screen, on the slides there, in order to do that. And it's pretty simple to use. But keep in mind also that if you use in RStudio, if you use a question mark and then the name of a function and then run that line, that down here, the way I have it set up in the help, you'll get the help stuff on it. You can also go here and search on it in the little window in the help window and get some stuff about usage and all this. Some of these, I will give you a little caveat on this. Some of these are really helpful. Some of them might as well be written in a foreign language. So just kind of, there's always, searching online and GitHub and Stack Overflow and all that. So, but a lot of stuff, especially if you just have if you can't remember exactly what the syntax is, it's really helpful. So there's a couple of things I want to do. One is we want to use this set seed function. So we're going to use set.seed, and I'm going to set it to 1, 2, 3. Now there's nothing special about that except that if you want to get into a really good argument with a computer science or math person, then tell them that random numbers that you get from a computer are totally random and they're excellent to use all the time. Because the truth is that they're not. They're based on an algorithm and they need a starting point. So the truth is that random numbers in the computer are usually random enough. So if you want to get really super random, then you can't use the computer, or you have to do some other things. So one of the things that we do is when we run a random number generator in a program like R, it will use the clock on the computer to seed the random algorithm. If we put in a seed value like 1, 2, 3 or 9 or whatever we want to put in, it'll start at the same point, which means that when we run this, we will all get the same results. So it's very handy to use set seed when you're developing a model so that you'll get the same results every time, or you'll have the same starting point, so you can better evaluate whether your model's getting better or worse. Because if it's got some random fluctuation in it each time, then you don't know if it's from that or from or it's actually getting better or worse. So we're going to use set seed, and I've got to remember to run it. Sometimes I'll type that in and forget to run it. And then we're going to create an object called train sample, and that's going to be our training data. And we're going to run the sample function. And the way we do this is we, let me just type this in here, 100 and 900. So what we're going to do is what this says is we have 1,000. We want to generate 1,000 random numbers, and we're going to use 900 of them in fact, if we come down here, you'll see this is the elements from which to choose, so 1,000, and then the number of items to choose from, 900. So this will create our train sample object here, and I didn't run that. And I'm going to look at str structure of train sample. And one of the things that you'll see over here in the console window is it looks exactly the same as what's down in my environment window. So I tend to use the environment window a lot. You can also, go down and minimize this. You don't have to look at it, but it tells you what things you have in memory down here, what objects in memory. So what this did was it created 900 random numbers between 1 and 1,000. And it's in this integer vector called train sample. So what we're going to do then is we're going to split those data frames. So we're going to create an object called credit train. And we're also going to create a credit test. But credit train is going to be the credit object, the data frame, and we use square brackets, and we're going to use all of the rows with the index that are in train sample and all the columns, so we don't put anything in there. Whoops. I want to make sure there's a space there for readability. And then credit test is going to be credit, and it's going to be very easy. It's going to be the ones that are not in train sample. So we use a minus sign, and that says not in train sample, but we leave all the rows. So let me run those. And you'll see now credit train just showed up down here in my environment window under data. And now credit test, and there's the 100. So we've got 100 and 900. Now your values for train sample should be the same as mine, 415, 463, 179. If they're not, it's because we have a different version of R installed, and on the next example, I'll show you how to take care of that. So we've done the table. We run these two lines, we get a proportionate table. And so you see we have in the train, it's about 70-30, and test, it's 65-35. So not too bad. It's a small data set. So if we had a bigger data set, then we could get a little better representation. So why 90-10 split on the percentages? That's just the number we decided to do. Whatever's appropriate, whatever standard you have. Usually though, we'll run anywhere from 2/3 on up for training, and then run some with some testing data to see how it works. So we might have 10 to 30% on the testing side. Again, a little experience goes a long way there. And maybe we get a little better results if we went 85-15 or something, but that's one of those things that's just one of those decisions that you have to make that's separate of the code and the stuff that you're actually doing there. So we now have training and test data, and we want to create a model. So we're going to use the C50 library. If you don't have that, then you can install it. So one way to find out if you have it or not is to run this command. And if it comes back and says you don't have this, it may even give you the option to install it. You can also look in this other window here under packages, and it's taken just a second. There we go. And you can come down the list, and there it's in my list. You probably don't have it in your list. It's alphabetical. And so you can then go, if you don't have it, you can go to install here and type in C50. And you can select that and install, or you can run this line, install packages. So there's multiple ways to get this in there, but you only have to install it once. When you want to use it, you can run library C50, or I can come over here and I can click this button, but I like to run the line of code. So I'm assuming that everyone is going to have to install that, but it won't take very long.
It kind of did it automatically for me, Mike.
Okay.
When I brought up this the decisiontrees.r file, it
Yeah.
said something about such and such libraries needed but not installed. Would you like to install them?
Okay.
And I went, okay, and
Yeah.
it ran through all that in the console. And,
yeah, you get that line up here at the top of the window. I get that sometimes when I'm moving stuff between computers, and yeah, that's the other way. I forgot about that. Thank you.
Automagic.
Yeah, if you load something that has, so you'll see with the other, you'll get the chance to load some other libraries. You could do that same way. So yeah, there's plenty of ways to get them in there. So it's not difficult at all. Almost every package that you load, you're going to get some kind of a warning. All it's saying is it was built under R version 3.6.2. I am currently running, let's see, I don't remember if it says it in the R Studio window or not. I think I'm running 3.7 something. Anyway,
Wasn't that it at the top of the window?
Doesn't really matter. What's that?
Wasn't that the version at the top of that window?
That's the R Studio version, but not the R version. R runs underneath R Studio. But yeah, I think it's 3.7, whatever. And there's a command that you can type to find out what it is too. I don't remember what it is off the top of my head, but I try to keep that up to date if I can. Another nice thing about R, as a little aside, is that you can have multiple versions installed on your computer and use different ones if you need to make sure that something is compatible with old versions or anything. So it's pretty easy to have multiple versions if that's something you need. I almost always just have the current one. And I'm only saying 3.7 or 3.8, whatever is current, because I had to upgrade it a week or two ago when we finished some research stuff. So everything we've done up here, we still haven't done anything with creating a model. So that's what we're going to do. And one of the nice things, and I think one of the reasons why R is used for modeling a lot, is that it's pretty straightforward with most of these packages. So we're going to build the simplest decision tree that we can. We're going to save the results in an object called credit model. And the way we do that is we call the C 5.0. We have to use 5.0. You see it shows up when you see 5 point. And we tell it what we're going to run it on. We're going to use credit train, that data set, but we don't want that, that last item, the default. Remember when we looked at, go back up here, the last column is default, and that's what we're going to try to predict. So we don't want that included in our model. Otherwise, we'll be using the result to predict the result. So the way we can do that is there are 17 columns in there. We put in -17, that actually excludes that one column. So that's a neat little shortcut that I like. And then we put in the, again, we could go to help and look at it, but we put in what is it that we're going to, the data we're going to use, and then what is it we're trying to predict. So we're trying to predict credit train $ default. And that will actually generate a model there in that split second. So let's take a look at credit underscore model. And I need to make this a little bit bigger. And this gives us just some general information about it. So you see there were 900 samples. That's our train data set. 16 predictors because we excluded the 17th. And so the tree is 69, I remember if it's levels or branches, but that's a lot for that amount of variables and stuff. But that doesn't tell us a whole heck of a lot. So we want to actually look at a little bit more, and all we have to do for that is do summary credit model. And now that gives us more usable data. Actually, we've got to scroll back up a little bit. And this one, thankfully, reformats when you make the window bigger. And I need to make it just a little bit bigger. There we go. So go back up here, and then now here's our results. So this is the actual tree. So this shows that if they had a checking balance that is either unknown or greater than 200 Deutschmarks, then no, it's predicted they're not going to default. And that is, it's been a while since I've looked at this. 412 they get correct and 54 they don't. I don't remember the numbers out here, but it gives you an idea of how many are going down that path. So if they're in the other categories, then they go down this path. So if they're in this checking balance, then we can look at their credit history. If it's perfect or very good and they rent, then yes, they'll default, and it goes on down. Now that's hard to read, so we're going to do a graphic version. But the other thing is that there's a lot more detail, and it looks like there's some potential overfitting in here because we have lots of these that just have very small numbers at the end. So this is a pretty detailed decision tree out of a small number of records, 900 records. So we're going to change that up a little bit. Now the other thing is this next line in the code is we're going to visualize the tree, but you're going to see that it's not much use. So it's going to come in the plots window. So I'm going to make that one bigger, and you'll see what's going to happen if you don't. So all we want to do is actually use the plot and credit model. And it'll take a second. There we go. And so you'll see, you get a plot of what that tree looks like, and it's pretty much unusable. It's just, there's so many different branches and things that for 900 records, it's not usable. Certainly not on a practical basis if you're talking about a loan officer in a bank actually using this. It's just impractical. So we're going to try to refine it a little bit. And we'll get a graphic later. And there are other packages where you can do other graphics with it. But down here at the bottom that you can't see because it's all garbled together, it gives you how many yeses and nos and the proportion and all this kind of stuff. So there's just so much that it's not much good. If you get an error in your console and the plot window, fact, let me see if I can generate it. You might get an error that says something about out of bounds or exceeds boundaries or something like that. Let's see if this actually produces the error. Taking just a little bit longer here. Did it actually do it? Yeah, it actually did it. Okay. But what'll happen is you'll get some kind of an error message in the plot window or in the console that says that you're something about it, boundaries or margins not exceeds margins or something like that. What it means is that the plot window is not big enough. And if you make the plot window bigger and then rerun it, it'll fix itself. You can refresh too. Another nice thing about the plots is, of course, these are the same, but these arrow keys here in the plot window, if you have multiple plots, you can go back and browse through earlier plots, move through them. So you don't have to replot if you need to see something earlier. So there's some really good functionality that's in RStudio. I like it quite a bit. The notebook certainly has its place too. So that creates a model, but it's not that that great. But let's take a look at evaluating and doing a little improvement in the way the model works. So the first thing, and this is the last thing we're typing in this file, is we want to make some predictions. So let's save that in credit pred for prediction. And what we do is we run a function called predict, and we tell it use credit underscore model. So we're going to run our data through that. So what data? Credit underscore test. And let's run that through that model and make some predictions and save it in credit pred. And you see that worked. So now we have some predicted values, but we also have the actual values because they were in the data set when we got it, right? That's why we had to use -17 to exclude that column because we had the actual results there. So we can compare the actual with the predicted results. And a really easy way to do that is with this Gmodels library. So if you saw that note up there about the packages and already installed them like Don did, then you already have Gmodels. You can always check, or you can run library Gmodels. If I don't have it installed, it will come back and say, you don't have that. Here I get that same warning. It's not a big deal. It's just telling you that, you know, it was built under a previous version of R. But if it works like that, then it's good. And there's this function cross table in there that actually will take this, the default here, the default column was the actual results, right? Credit pred is the predicted results we just did. And then we don't want to see, we don't need to see chi-squared. We don't need to see a couple other things. And then these are some labels that we're going to put on it. So best thing is just run that. I'm going to make this, the console a little bit bigger. So if I run that, and my computer's really slow, it should have banged that out pretty quickly. So this actually gives you what's called a confusion matrix. So this up here where it says cell contents, this tells you what's in the cell. So it's the number in the cell. So there's actual no's and predicted no's. There's 55. And then that divided by the total is below it. So 55 out of 100 is 0.55. Gives you our total observations, and that's down here too. But this gives you, like I said, a confusion matrix, and this left to right diagonal going down are the correct ones. So it got 55 no's correct and 15 yeses correct. And then the other diagonal in this 2x2 are the wrong ones. So this first one here, it was actually no, they wouldn't default, but it predicted that they would. So that would be a false positive, because what we usually consider the positive result isn't necessarily good. It's just the thing that's different from what we normally see by default. There's a little bit about that in those slides. So if it's was actually a default, but it predicted that it wouldn't, then that would be a false negative, because it predicted the negative condition and it was actually positive. So mistakes are this left to right up, and correct ones are left to right down. So, and that may change depending on what our positive state is. Just the way that ours is set up here, that's the case. And then of course you see all of the actual defaults. There are 65 and 35. Remember, we saw that in our early proportions. And then it's the predictions. It predicted 75 no and 25 yes. So the big question then from the standpoint of the analysis is that okay? Is that accurate enough? Probably not. But the other thing is that what is it that we want to avoid more than anything? And that depends on what the context is. If we're talking about diagnosing cancer or some other medical thing, then we probably want to, do we want to avoid false positives or false negatives? I don't know. That depends on what we're talking about disease-wise and everything. That's been a big discussion with COVID testing. Would we rather have somebody show positive when they're not, or vice versa? So that's a decision that has to be made. With credit, it also has to be made. Where do you want to take your gamble? Because remember, all models are wrong, but some are useful. And so we're looking for a useful model, but there's no way that we can avoid all mistakes. So one of the ways that we can do that is that we can make some mistakes more costly than the others. And there's something called a cost matrix that we can introduce to the model. Again, there's more about this on the slides, but what we do is we give it some values to say, let's make something more costly. So in our case, what we're going to do is we can just, I think we can get through this, Don, if it's okay, in 5 or 10 minutes, and then take a break then. That's all right?
It's on you, sure.
Okay. So we want to, what we're going to do is we create this, and like I said, all this code is in here. So we're creating, we see what matrix dimensions look like. We just set this up to our predicted and actual values, and then build a matrix, which is another data structure in R. And so we have this error cost matrix now, and you see it's just a little 2x2 table. It's lined up a little bit differently than our results, but the idea here being that if we don't want to miss a false negative there, so we make, let's see, actual yes, predicted no. So we don't want to miss, we want to make the false negatives more expensive, because we don't want to accidentally loan to somebody that's going to default. And then we have a little bit of a cost going the other way on a false positive. But what those numbers need to be, that depends on the modeling, and it's really comes down to business rules. So what we have is we have this matrix. So we're running the same model code as we did before, just with this costs option added, and we add that cost matrix. So let's run that. And then we make the predictions again, and then run the cross table again. And you'll see that our results are a little different. So now we have 67 that we got right. before we had 70 right. So it's a little bit different, but you see this number has come down tremendously from 20 to 7 because we decided we didn't want to make mistakes in that category. So we can make adjustments in the model in order to make some decisions cost more than others so that we can try to avoid those, whatever it is we're trying to avoid. Now, if we're just deathly afraid of that, then instead of a cost of 4, we can make it a cost of 9 or it's just a matter of getting experience and like I said, the business rules. Of course, we also made more mistakes here where we thought somebody might default, but they didn't. So we missed out on some opportunities, but we were really trying to avoid these situations where we said, no, they're okay, and we loaned them money and they did default. So it just depends on your business rules and what kind of an approach you want to take. So another thing that we could do, where we'll wrap up here, is we ran the easiest model we could run, just running all of the variables. And if you remember at the end of the output for the model, there was a list of all the variables and how often they were used in there, and some of them were barely used at all. So we go in there and just pull out the ones that are the used the most in here. And I don't remember why I have this job comment on here. I guess I had included that once and then took it out. But this is just re-specifying with what, 1, 2, 3, 4, 5, 6, with 7 variables instead of 16. So I'm just setting that vars object to these strings, and then I'm going to run it with those columns and all the rows, and then do default. So running basically the same model, just specifying the training data a little bit differently. And then we can look at that model. It's still running. So there we go. So the tree is a lot smaller, 43 levels. That's still probably a little bit unwieldy. But this attribute usage, this on the first time, it was a really, really long list. And some of the stuff was down it wasn't used much at all. So you'll see here, we have our 900 cases. We have 150 errors. That's this 124 plus 26. Remember, those are errors. These are the correct ones. So 16.7% errors. I think that's better than we were doing before. Gives us a little bit more. And we look at the tree, and it's still pretty good size, but it's definitely simpler and easier to use than the ones that we were using before. And then if we plot it, we'll see something that's a little bit better than before. So it's not quite as cluttered. It's still cluttered, but we get a graphic view of it. But this is just the basic plot function on that model results. There are other packages out there that can print something or plot something that's a little bit easier to look at. So that's, in a pretty short time, decision trees, something that we normally would spend several hours on, but just kind of an introduction to them. And then, maybe you keep tweaking this. Maybe you look back at this and say, well, this is better than I had before, but one of those things, I think purpose was one of the factors that wasn't, purpose and housing, maybe they don't matter. Maybe if you take those out, maybe you get a more accurate model. I don't know, but you can try a bunch of different models and see what works the best. But it comes down to, you're going to make some mistakes. So where do you want to make those mistakes? Or at least where do you want to bet that you're going to make those mistakes? And then you can't try to get to 100% accuracy, because if you do, then you've got an overfit model, and it's just not going to work out in the wild when you try to use it on new data. But that's one of the reasons why we run it against the test data to see how much how well it's worked. We'll also sometimes have it work on another set of data that's completely unrelated to give us something else to gauge it against too. So I think that's a good place for us to take a break, and then we'll come back and talk about the k-nearest neighbors classification, and then the k-means clustering after that. And we'll talk about them in general, and then get to the code. There's not a whole lot of typing that we're going to do in those other ones. I just want to show you some of the capabilities. So.
Okay, so reconvene about 9:50, 9:50. But Mike, if you've got, I need a break. But if you've got 30 seconds, can you scroll up to where you declared and then looked at the properties of the credit test data frame? I'm getting an error anytime I use credit test, and when I looked at the properties, okay, minus train sample. I didn't put the comma
Yeah.
on the second one. I'm sure that's going to fix it. And then when I do the property of credit test now, it was telling me, there you go, bam, fixed it. Okay, cool. I missed a comma. There you go. Blew my whole wad. All right.
And you can also, I don't do this too often, so I don't remember, but it's you can run a bunch of code. Well, you can highlight multiple lines and then hit run, and it'll run all that stuff. There's also some options where you can, I don't remember. I tend to either run it one at a time, or I highlight a big block and run it.
Yeah, I missed that comma in the after train sample and that goofed up everything I ran involving that data frame after that. Cool.
Okay.
See you back here in a few minutes.
9:50, you said.
Ish. Yep.
Right. Okay.
And we're back.
All right. So the decision tree was a supervised learning technique because we had a target we were trying to predict default. So another way that we can do a classification problem like that with a supervised learning technique is k-nearest neighbors. It is basically considered, it's based on the idea that things that are similar, that are close to each other, tend to be similar. So the idea being that let me just get to, it looks at it to find things that are similar. It looks at the nearness of the data points. So it just takes the different, uses distance to do that. So it takes the difference between the data points and uses that as a distance measure. So there's a lot of different ways of doing it. Just simple Euclidean distance, like this drawing of the triangle there, shows is what we're going to use here. But there's another one that's commonly used called, I think it's called Manhattan distance, where it's like distance if you took a cab in Manhattan where you had to go, up 2 blocks and over a block and then over. You can't go directly there. You take it a little differently. That's another calculation that's used, and some others. But Euclidean's pretty good in most of the cases. It's just what's the straight line distance between the points. One of the things about distance is there are no units, and there's no interpretation. So you get a number, you get 147.6. It has no meaning except relative to other distances in the same model. So that's something to keep in mind. There is an example in here that shows you how it's calculated. Of course, the squares and the square root are in there to get rid of any negative signs. and get an absolute result. You'll see here the calculation on 3 different variables: age, years at address, and then residential status. So you can do it on different kinds of variables. And then what we do is we look at the calculated distances and we find the points that are the closest. So we find the ones that are most similar that way. They're the nearest neighbors. That's where that comes from. So when we're looking at unlabeled, the ones that we don't have a result on, we compare them to like training data to create this model that we do have results on. And so we know which of those points are closest, and then the unlabeled ones, the ones that are most similar to, then we assign it to the same classification. And we can look at the different K numbers. The K is just the number of neighbors we're going to look at. So we typically use an odd number so that if there's any kind of, we don't have ties with the distance calculations. And I'll show you here an example real quickly. But K is based on some different rules of thumb and stuff, which we'll talk about too. So here's an example with just majority voting. So we look at trying to predict David. And so the way we do it is we calculate the distance between David and all the other points. And then we look at what is K. K is 3. So we look at the 3 smallest distances. And then we look at what are they classified as. So the 3 smallest distances, I thought I might have some animation in there, are John, Rachel, and Nora. So John, Rachel, and Nora. So the values of those target variables are yes, no, and yes. So there's 2 yeses, 1 no. So we would predict yes for David. But you see with that data that those values are all over the place. Age, income, and number of cards are on different scales. So one of the ways we handle that is going to really skew the results. So we normalize it. So we put it all on the same scale. We can use from 0 to 1. We're going to use that in this example, and we can also use a Z-score scale. We're going to use that in one of the examples. But the idea is we just convert it all to the same scale. Now, if all of these values were on the same scale, if they're all like 1 to 7 or they were all less than 10 or something, then we don't have to worry about it as much. But because these values fluctuate all over the place, we want to make sure they're on the same scale. Otherwise, the number of credit cards that a person already has might actually be the best predictor. But because income is such a large number, it might just completely overshadow that. So we want to make sure that we don't do that. So here's just an example with the normalized data, and the prediction actually comes out different if we normalize it. So we won't worry about that here. But this is the distance in that first example, and I just did this in Excel, and then looked at normalizing those different data points using this equation. And this is the equation that we're going to use to normalize too. It just puts everything on a 0 to 1 scale. K nearest neighbors is considered a lazy learning technique because there's no abstraction steps. So you really don't create a model. There's no equation or anything comes out. It just takes the training data and it does these calculations, these nearest neighbor calculations every time. So it really isn't learning anything. So that's why it's lazy learning. But it does find these patterns out there. So it's very helpful. So we're going to look at some breast cancer data, Wisconsin Diagnostic Data Set. It has a lot of different scans, and it has 32 features. So it actually has the mean, standard error, and highest value for all these characteristics listed here. And then the diagnosis, M and B, is what we're going to try to predict. So lots of stuff going on here in this data set. And then here's just a little bit. We use the class package, which is short for classification. And we're going to need the factor data type again. So we can do some, we're going to drop the ID number. We're going to do some splitting, and we're going to normalize, and then use this lapply function, and then predict the model. Here's some generic stuff about the model. And then the thing is, you might wonder, what are we going to use for a value of K? Well, there's some rules of thumb, but the biggest thing is we usually do look at the square root of the number of examples in the training data. So in our case, we're going to go with 21 because it's based on the square root of 469, which is what we're going to use for training data. And then we're going to use 100 for test data. And then we can look at different values of K and see what tends to work the best. But again, if we keep going at trying to get 100% accuracy, we're looking at overfitting our data and winding up with a model that just doesn't work for us. We're going to look at that cross table again, and we'll talk some more about this. I already talked about this with the last example, and then we're going to do some transformation and a couple other things. So like I said, this is all in there for your reference, but let's go to the code and take a look. Now, I don't need to change my working directory. One of the things that I want to do is you'll see down here in the environment, we have all these different variables and things in the environment, lots of history. I want to clear that stuff out because I'm just going to keep filling up RAM on my computer. So there's some commands and stuff, but the easiest way is this broom icon. It clears all the objects. So I want to go ahead and remove all the objects. So now all that's gone. There's a broom icon up here at the top of the console, top right. I'm going to go ahead and clear that up. And there's another one here on the plots. I'm going to clear that up because we don't need any of that. And that's just filling up memory. So just going to clean that up. So the first thing I want to do is to read this data, and it's in this file. If you need to change the path on your machine, then go ahead and do that. But then we'll see what it looks like. And in this case, diagnosis is the second variable that's in here. I don't know, can I make it big enough to get all those off? Yeah, just barely. So you see we have an ID number, and then we have the diagnosis, which in this case was read in as a factor by default. So it didn't have to specify that, but we could always, if it wasn't, add that strings as factors. It's the only one that's not a number in here. And it only has the 2 levels, so it's read in as a factor by default. But we could always convert it to if we needed to. But that needs to be a factor because we're going to predict it. So you see all of these different, the first group are the means, and then the SEs, I think it was standard error, and then the worst case. So that's the data that we're going to use. So 569 observations of 32 variables. So let's take a look at, we're going to predict that diagnosis variable. So let's take a look at this. Let's actually create an object called counts. And we're going to do that table function that we did before. Use that table function on W, B, C, D, whoops, D, $ diagnosis. And then, I can run that. And then I want to take a look at what's in counts. So we have 357 benign and 212 malignant. And then on this line, my line 26, where I have that proportions of counts, let's do prop.table like we did before on counts. And it'll just give us the proportions. So we have almost 63% benign and 37% malignant. So it's roughly 2/3 and 1/3. So that's just the one column that we have that we're trying to predict. So what are the other columns? If we use this call names, we can see what all the column names are. And we've got those there for reference. We can take a look at the summary function, and we get basic stats on all of them. But that's an awful lot. So let's run that next line and just look at these three values. So you see for radius mean, area mean, and smoothness mean, look at the different ranges. Look at the minimum for radius is roughly 7. I don't know, 7 what? I don't know. I think it's millimeters, but area mean, the min is 143 and smoothness is 0.05. So these are on very different scales. If you compare the min and the max across those three. So we definitely need to normalize this data, or else the area is going to dominate. Smoothness is going to have no effect, really. It's going to just get lost in the model. So I like this example because it shows how the data definitely needs to be normalized. So another thing is we don't need the ID column. So I'm going to change that. I'm going to save this as WBCD by saying WBCD and the square brackets and then saying -1. Remember, we used that last time. That just says save everything to back into WBCD without the first column. If we take a look at the structure of WBCD, we'll see now that the ID number is gone. Because at this point, we just don't care about the ID number. The individual rows don't matter. We're looking at what the effect is with the entire data set. So I think, yeah, that's really all we're going to type in this. So the rest of it, we'll talk through what's going on. So we can create our own normalization function. So that's what this does. So this identifies a function called normalize. It creates it. And this is just an inline function. So it's inside these functions we write in R inside the curly braces. And they can be multiple lines, and we'll see one of those later. But this is just an easy little equation. So we just have this in here. So it just takes in a value, and actually it's the column, and we get the minimum and the max, and because this is vectorized, and so it's going to get the min and max and do this calculation just like that equation that was on the slides. Here's another thing. I'm going to make this environment window a little bit bigger before I run this line. So you see, we just have that one data frame, WBCD, that now has 31 variables, not 32. And if you weren't aware, if I come down here and click on this, it will open up a spreadsheet-like window, and you can see all of the different columns and the data up here. Opens a new tab up in this. So that can be, if you really want to take a look at the data, that can be a handy feature too. But I'm going to run my line 41 there, the normalize function, and you'll see now I have a function showing up down here in the environment window. So that shows up. Now we want to test it. Let's test it on these different values, and the results should be the same. So we'll run the first line and the second line, and the results are the same. So it looks like our normalize function is going to work okay. So this is the way that we normalize that data. I'm going to save it in a new data frame with that _n on it. And then we're going to run this lapply function, which runs the, it says take these columns and apply the normalize function to it. And it comes back as, what does it come back as? It comes back as a vector or list, or I forget exactly what it is, but we need this as data frame to make sure that it comes back in data frame format. And we're going to save that as WBCD_n. So this is another example of lots of stuff is going on here on this one line of code because of everything that's provided in the different libraries. So if I run that, and now you see I've got WBCDN 569 of 30 variables down here because we didn't want, we left out the first column by not including it in the list because it's the diagnosis column, which we didn't need. So now I can click on WBCDN down here and see what it looks like. And now we'll see all the data looks a lot more uniform. It's all on, you know, here's the areas were big before. Now it's all 0 to 1. So we can make sure that that worked. Here, this first line, 55, is the summary of the original data, and the second one is on the normalized data. And so let's run that first one. And to make that a little bit bigger, I'm going to run that again so it shows up on one line, and then the second one. And so you'll see that first one that we looked at that had everything on wildly different scales. And now the second one, everything is from 0 to 1. Min to max. So it's all on the same scale now. So now we can get we can be sure that we get a better result by looking at the neighbors. So we're going to create training and testing data sets. This data is actually already quote unquote randomized. So we're just going to use the first 469 rows for training data and then the last 100 rows for testing data. So I'm going to run those, and now I've got those two data sets. And then the way that this works is that we need to get the diagnosis data out to use as labels for the training and test data, because we have to specify those separately. So here again, we're going to bring just that one column, the first column, for those specified rows. And you'll see this also shows up here now. It's under values because it's just a vector. It's not considered a data like the data frames are. So now we have everything that we need. So I think most of you have probably already installed that, which you can do with code like that. You can do down here again, or you can do it when you open up the file and it said that you were missing some stuff. So I went ahead and implemented that, or hooked up that library. And this is all we do. Again, the actual model building part is pretty straightforward with the package that we have. We call from this, and there are other packages that do k nearest neighbors. This is just one of the more common ones out of the classification class package. So we call the KNN function. We tell it what the training data is using the train keyword, the test data using the test keyword, and then what's the class, the classification, the label, what is it we're trying to predict with the CL keyword, and then we give it a K number. Now K, you might remember, you saw briefly on the slides, is based on the square root of 469, which is the number of training rows we have, and that was 21. So this actually runs the model.
So we got,
yeah.
When we were extracting the labels, we were using the original data frame, not the normalized one. And I was wondering if that made a difference for anything.
No, the labels are the same either place. In fact,
the difference might be that we left out a column, didn't we, for the normalized one?
We left out that first column, the one that had the diagnosis in it, because the diagnosis is an M or a B. So it wouldn't have been affected by the normalization anyway, but we didn't need it in the normalized.
But that's why we would have to use the original data frame, because that's where
because it's not in the normalized database, and because we don't want it in our modeling data. So the other thing, we use that G models library again, and the cross table. This should be on another line here. And we get that confusion matrix of results. And so we'll see that actually looks like 98 of them are correct and only 2 are wrong. So we predicted 2 were benign when they're actually malignant. So I think, and we have discussions on this in class, and we're not medical people, but it would seem that predicting that you don't have cancer when you actually do is probably the worst outcome that you can have. I don't know. If you predict that you do when you don't, you may have to do extra testing and stuff. But again, it depends on the context of the problem and what are you trying to avoid. But 2% errors out of the total, that's pretty good. So that is just looking at how can you classify data by looking at what is it most similar to. So when you bring in this case, the training data, it looks at each row and the different characteristics and looks at the 21 points that are closest to it using that distance calculation, and then looks at the majority, at least 11 of them have to be classified one way or the other, and then that's the prediction it goes with. And in this case, in this topic arena, it seems to be pretty accurate. Let me go back here. So there wasn't very many lines of code. In fact, a lot of that stuff was just getting the data ready to go, and actually was able to be 98% accurate. But you've got to be careful because remember, you've got to normalize the variables so they're on the same scale. I have not run this. I need to run this at some time without normalizing it. But that's just one of the standards that we do. Any of the techniques that rely on distance need to be normalized. So K nearest neighbors is one of them. Otherwise, it's going to, if some values are higher than others, it's going to be thrown way off. You have to be, yeah.
For the previous, for the decision tree model, we were able to kind of weight things using the cost matrix. And I realize it's different here, but I was wondering if the nearest neighbors model had anything that
where you could, you could make
one way or the other.
Yeah, make one more important than others. I believe there is a way to do that. I have not worked on anything like that specifically. The other thing is that kind of goes against the thinking of let the data speak for itself. So if the data comes out and like in this example, it turns out that area is one of the more important factors, then what good does it do to make something else more important? Or if we were doing a credit score this way, if we come out and it turns out that
wouldn't we be able to do it basically by the normalization?
Well, the normalization, it's going to make to where all the distances are going to have the same weight. So I guess we could do it before put them on a different scale. But I'm trying to think of why we might want to do that.
Well, I'm thinking of, I always forget what the name of it is, but there's this concept in physics, especially when you get into the nano and the micro kind of environments, where certain physical factors have very little weight or applicability, just because of like they represent something that is squared. And then the example I'm thinking of is if you drop a bug from like a 3-story building, it's probably not going to get hurt too bad if it hits the ground. But if you dropped a baby, which has a lot greater weight, it's going to get badly hurt. So I'm thinking of that kind of physical dimension. And when we're looking at area, I was kind of wondering, like, do we normalize the literal area value, or maybe would it be more prudent to normalize like the square root of it? Because then you would kind of get a representation of like just like a linear instead of an area measurement.
Yeah. I can't answer. I don't know the answer to that. It would be interesting to try and see if you get good results with it. I'm sure there are people in labs, medical labs, looking at this kind of stuff that are looking at those different options.
Well,
I don't know.
Is there a way to apply the normalization functions to specific columns, I guess?
Oh yeah. Yeah, you could go in and
so where we did it, we said apply it to columns 2 through 31. So maybe have like 2 sets of columns specified.
Yeah, okay. we could do it. Yeah, we could do it different ways. We could do that one separately and apply a different function to it. Yeah, it's just a little code to work it around. So you could try that. You could also create a column that was the square root of the area once. Just introduce another column into the data and normalize that, like any of the other data columns, and see how that works. So there are some different things that you could do to play around with it. But again, you've got to be careful that you don't wind up overfitting and you wind up with a solution that works great with the data that you have, but then doesn't work out there on other data. One way to test that is you set aside some data that you don't even look at until you decide what's your best model, and then run that through and see how good a job it does.
Like an ultra test.
Yeah, a lot, and there's different names for the different data sets, but if you're really doing a big analysis and modeling, you're going to have a training set, a test set, and then an evaluation set. And so we're talking about training and test, and you'd have some other data that you run it against, but you don't make any decisions. The test, you might run it and say, I can go back and I can change, or I can look at the square root of the areas. And so you're using that to refine your model, and then you run it against that evaluation set to see, okay, so now how does it do on this? And I've made my decisions, and you're trying to test what your final model looks like, and you're hopefully not making a lot of changes at that time, because you're going to wind up even overfitting to more data, I guess would be the answer. But so you have, and again, we got 569 rows. When you've got thousands or millions of rows, it's a lot easier to set stuff aside. Just be sure to do it randomly so that you don't wind up with data sets that have too much or not enough variance inside the data sets. There's lots of stuff that you can do here and modifying the data. And maybe it turns out that area just isn't a good predictor, and so you just don't even use it. So there could be lots of different combinations and things that you can look at.
Thanks.
Sure. So I guess we'll head on into the k-means clustering. Now, k-means clustering is unsupervised, so there is no target variable. So k-means and the unsupervised stuff are just are like, let's find a pattern and see what's there. We're not trying to make a prediction. We're just trying to see what's there, basically. So it looks for natural groupings. And I actually used this with some colleagues on some research a few years ago. We were looking at the most highly cited model in information systems, the technology acceptance model, and doing a meta-analysis. And we had over 900 studies that were in our final data set. And each one of them had a type of technology that it worked with. And this went back to the mid 80s. So you can't talk about 900 types of technology. You need some kind of categories for them. So we did essentially a cluster analysis on that and generated like 20 or 25 categories of technology so we could talk about them instead of having to talk about all this stuff. So the same thing, you might find groupings of customers or products or something else based on characteristics that maybe don't just jump out at you. So it's really, you're really creating knowledge with this kind of thing. So you're trying to learn stuff that you may not have already known. Sometimes cluster analysis is used as eventual input into a classification problem. So we can go out and let's identify some clusters in our customers, and then when we get new customers or potential customers, we can identify which cluster they might be a part of, and then we can adjust our marketing towards them that way. And maybe we check clusters regularly, or we do something and we give them names. But it can be that first step into what becomes a classification problem down the road. So k-means is similar to k-nearest neighbors in that k is the number of clusters, the number of clusters we're going to try to create. And we figure that out before we run the analysis. It's not a huge deal. We can try different clusters to see what's going on. And we do use distance to assign those points. So it also needs to be normalized. And I didn't mention, but I guess it should have gone without mentioning, was if we're doing a distance calculation, like with k nearest neighbors, it has to be numbers. So we can have categories still, like we can have some different categories, but we have to have them as numbers. But it doesn't work that great as well as we do with having actual numeric values. And then k-means clustering, like k nearest neighbors, does not like missing data. So we have to do something with missing data before we actually look at it. So the clustering is a little bit different. The idea is we select a bunch of points, however many the k is, as our initial centers, and then we assign the points to that nearest cluster center, and then we recompute the cluster center, and then we go again. So let me show you graphically here. So step one here on the left, we have 5 different points, k equals 5. So with the blue diamonds, those were the points that were chosen as the cluster centers. Then we calculate the difference between that cluster center and the nearest points, or actually, I guess, the points and the nearest cluster center, and then we assign them to the cluster. So here, this hot pink, whatever it is this cluster, there's just a couple in this one, and the green cluster, and so these are the clusters. Then once we've assigned them to the cluster, now let's recalculate the center, and we see the center moves. So the center moves quite a bit in each one of those, and then we do it again. And so each time we move the center, we recalculate and then go through the exercise again. So it will eventually converge on a solution. Sometimes it'll get to a point, it'll fluctuate a little bit back and forth, but we have ways of ending that. There's actually some great examples, automated examples or animated examples on online showing how it works. And I forgot to put those links in here, but you can, if you want to see an animation of going through all that, you can find that pretty easily online with a search. So the k value, like I said, we have to figure out what it is. It's not based on these square roots or anything, but we can do it 3 ways. One is domain knowledge, that we just know that in this domain that it's common that we have 7 clusters. So let's look at it. We're going to use kind of a domain knowledge thing in this example. It could be business requirements. We could say, you know what, we want to run 4 different marketing campaigns for this next year. So we need to break our customers into 4 different groups. So that may determine the k value. Or if we're trying to find a little bit better k value that gives us the best results, then we can use some experimentation, and I'll show you some of that. But one of the big things is, and I'll show you the elbow method. But the big thing is finding the exact best value of K is usually not that important. It's more important to get something that you can use. So you don't want to get down the rabbit hole of trying to find that best K, get that extra couple of percent. So you get something that's good enough and go on is usually the best way of doing it. So there's some different k-means functions. There's a stats package that has k-means. We're going to do that one. We're going to look at teen market segments from some social networking users. And actually, I believe this is out of that book I use as a text, and I think this is research the author did himself. So there's 30,000 different data lines in there. And these were all kids that were graduating from high school in the late 2000s. And it has a few pieces of data. And then they looked at these different terms for 5 interest categories. There are 3 issues with the data. There's missing values in the gender column. There's outliers of missing values in age. And then the data needs to be standardized as well. So I'll show you a little bit more when we looking at the data on what it actually, what some of those issues actually look like. And I am going to sweep these things clear. Clear this stuff out. And let's see, okay. So I'm going to load that data. See 30,000 observations of 40 variables. And so let's look at what does that data look like. So this is actually a better way to see what's there. So we have the year that they're graduating, which should be 2006 to 2009. We have an F or an M, female or male, and you see right there, there's an NA, and NA is how R represents a null value, a truly missing value. Pandas was NaN. Python itself is none, if I remember right, and it's NA in R. So there's at least one missing value in there. And then the age is numeric, so it's a float. You see we've got some decimal ages that are, if I remember right, is the number of months or something. I don't know. It really doesn't matter a whole heck of a lot, the detail on that. It's in the descriptions in places. And then we've got these terms, everything beyond age. So we've got grad year, gender, and age, and then everything else is terms that were text mined from social networking posts. So it's how many times these terms were mentioned. So this person in the third column, 69 times, friends mentioned 142 times. So we don't have a whole lot of them up here, but it goes all the way down to some of these other terms. And then we've got, church and blonde and Hollister and sexy and all these different terms that they might have that cover a wide range of characteristics. And what this model is going to do is to cluster them based on how many times these are used in their different profiles. Friends actually, I think, is the number of friends that they're connected to or something. It's not the mention of the word friends, but it's the same thing. So we're going to look at the frequencies on that stuff. So we said going in that we had some problems with gender. So let's take a look at a table on teens, because that's the data frame that we've loaded in, and then $. And I haven't mentioned, but you do, when you get the $, it'll tell you the different columns that are in there. And so you'll see 22,054 female, 5,200 plus male. But there's supposed to be 30,000 rows. So if you do some quick math, you'll see that there's got to be some that are missing. So I'm going to copy and paste that because I'm going to be efficient, not lazy. And I'm going to add an argument here. And we're going to say use NA. You see that come up there as that option. And the argument that we put in for that option is, and I want to use the double quotes just because I try to use that all the time in R. Use if any. So we're going to create a table of the values, but we're also going to create an NA table if it has any. And so you'll see there are 2,724 NA values. And if we add those up, then we'll see that that gets us to our 30,000. So one of the things that we want to do is let's create an unknown category or an unknown value column, and let's do all the NAs. We'll make it to that unknown. The other thing is that in this model, we want to create dummy variables for gender because it's a categorical variable. So dummy variables are just, instead of having one column where we have male, female, and unknown, we would create a column for each of those variables, and then we would have a 0 or 1 for whether it was there or not there. So we'll see that. And there's no, I guess I didn't have anything in the slides about that. But what we also do then is we create one of the categories is going to be a reference category. So in this case, we're going to use male as a reference category, because if we have a column that's male 0 or 1, female 0 or 1 for there or not there, unknown 0 or 1. If we know 2 of those, we know the other one by default, so we can leave 1 out, and that's our reference category. So we're going to create a teens female and a teens unknown column. So we're going to use this function here called if else, and it works. If you've ever used the same type of a function in Excel, it works the same way. You give it a condition, and then what does it do if it's true, and what does it do if it's false? So what we're going to do is we're going to create a new, I cannot type teens for some reason. We're going to type add a new column called female to teens. So teens $ female, and then assignment operator. And we're going to run this if else to give it a value. And so we're going to look at teens $gender. And we want to say, is teens $gender equal to female? Well, we use 2 equal signs when we're using checking for equality. So is it going to be equal to capital F? And we also want to make sure that it is not which is the exclamation, null. So we use is.na and teens $gender. So let's make sure it's female, it has the F value, and it's not a null value. So that's our condition that we're checking. Now, if it's true, then we want to set this new column, this new value, teens female, equal to 1. And if it's false, we want to set it equal to 0. So we're creating anything that says, any data point that says has the F value for female is going to be a 1 in this column, and a 0 if it isn't. We can also create teens $no _ gender, another new column. And we're going to do that, but we're going to, in this case, we just want to check to make sure that my actually, I can just copy that last half, put it in here. So we want to make sure wherever it's null, then let's make this a 1 and make it a 0. So if I run those, and then let's take a look at, so that was the first table that we saw. So now let's look at, are there any NAs in the female? No, there aren't any in there. It's 0, 1, and you see our 1 amount here agrees with the number of females in the first one. And then in the no gender column, we have a 1 is the 27, 24 that we're missing in the first one. And then everybody that is not in the no gender column is this 27, 276, which are females and males from that first column. So with just having the female column and the no gender column, we've got everything covered, because we know if both are 0, then that's going to be the male column. So I think we did some dummy variables in the pandas stuff, but it was all done automatically in the package. Here we create our own like this. So we also need to prepare the age variable, but I'm kind of thinking it might be a good time to take one last break, and then we can come back and finish this up. Does that work for you, Don?
Can do. Come back
Okay.
10:50.
Okay, 10:50 works.
Roger.
All right.
10:50. All righty.
Okay. One thing I wasn't real clear about was the reason why we have to, in assigning this female to 1 and 0, why the checking for the F, and also that it's not a null. The reason is actually for the 0 part, for the false part. So this is how we get the males in as males and missing as 0. So if you go through it, remember, if it's a logical statement with an and, then both sides have to be true. So if it has an F, obviously it's not null. But if it doesn't have an F, it isn't also null. So it can be wrong because it's an M or null. So that's why that compound statement there, that might seem a little bit overly complicated, but it's just so we get the nulls and the males as zeros in the female column. So it looks like our gender recoding is in good shape. But let's take a look at the age variable, because it said going in that we had an issue with the age variable, and we can actually see that pretty quickly. Let me run that again. So we have some missing values, but we also have a max value of 106.9. So there's obviously something wrong in the age value. We only want teenagers. So do we have any others that are 20 or older? We don't know, but we can eliminate those. We can eliminate those outliers. So let's take a look at that. So what we're going to do is we're going to recode teens $age. So we're going to change the value that's saved there. We're going to use that if else again. So we do the logical condition that we're looking for. So we want teens $age greater than or equal to 13, which I don't remember if we have anybody at that low, and we want them, we're going to use another and, we want them less than 20. So teens $age less than 20. And so that's our condition. So let's find everyone who's actually a teenager. And then what do we want to store there? Well, how about we just store their age from the column? So let's keep that. If they're not there, then let's put in an NA value, because we're going to not worry about those NA values. So this, I run that and we're good. And we run a summary on teen age, and I should have made this bigger. So now we have a max of 20, as we would expect, and it's running in the range that we wanted. Oh yeah, I didn't even notice we had a min of 3 before. So we still have, we actually have a lot more NAs, but that's okay too. So we want to clean, find out where those means are. And this actually doesn't work if we just try to take the mean of that column, because of all those NA values. It just gives us an NA. So if trying to take the mean with NA values just means that it's not defined. So, but if we do it this way in this next line, line 49, we say NA.RM equals true. RM is to remove the values, or which it just ignores it. Remove missing, I guess you can, that might be what it actually stands for, but that's, you can think of it that way anyway. So the average age in our data set then is 17 and a quarter.
Does the summary do that by default then?
Like I said,
yeah, it does in our calculations there. If we want to do it specifically though, we've got to invoke that option. So one of the ways that we can work with this is get average age by graduation year in order to fill some of that stuff in. So we're going to group it here. We're going to use a function called aggregate. And you see it splits the data into subsets. And so we tell it what data and what subsets. So the data is going to equal the teens data frame. We specify age and then the tilde, which is hard to see on my screen, but it's the upper left-hand corner of your keyboard, left of the 1 key. You have to use shift. It's that little, you know, it'd be an ñ in Spanish, but on top of the N, and grad year, that is one of the standard operators that's in R when you write equations. And what that does is it says we're going to look at age and we're going to group it on grad year. So we're going to look at the mean, and we are going to ignore the missing values. Let me go to a new line. We're going to ignore those missing values to find out what the non-null average is. And so we'll see, that's about what we would expect, right? The ones that are graduating further out are the youngest now. So it's about a year in between each of those groups. So remember, you know, we can use help on anything with a question mark. AVE is not just an average, it does more than that. We could also use that on aggregate or anything. This group's averages over level combinations of factors. So you can see some of the things. So there's a lot of functionality in there. We're going to use that function here to calculate the average age for each graduation year. And this is our statement how we're going to do that. So we tell it it's the age, it's aggregated over the graduation year, and then we're going to run this inline function, which is just, let's take the mean and don't include the missing values in there. So all this does is it creates av age. You see, it's an average age column for each, or a value for each line out there based on their graduation year. So students, or the data that has it, the kids that have an age will have an age column, and they'll have an average, about this average age. And then the ones that don't have age will have a null value or an NA in age, and then we have this average age. So we want to put this average age in to take the place of the null values. So that's why we're doing this. This is a it'll be our little assumption, is that if somebody's age is not there, then we'll just substitute the average age for people in that graduation year, and that should be close enough. So we're going to write a little bit more code here to look at teens age. And we're going to once again use if else. And so our condition that we're going to look at is we want to see is .NA, so is a null value in teens $age. So if there is a null value there, then let's put the value that's in the AVE underscore age column. Otherwise, let's leave the value that's already in teens $age there. I know the syntax may be a little odd, but hopefully the logic makes sense, right? So let's take a look. If the age is missing, then let's put the average age that we just calculated for that graduation year. Otherwise, if it's not missing, if that's false, then let's just leave their age there and we'll be fine. So now we shouldn't have any missing values. So if we run the summary, let me make this bigger. see now we had missing values out here to the right that had NAs, and now we don't have any. It also really doesn't change the mean or anything because we're using means to put them in there. So we filled in those values. Shouldn't really affect the results at all, but we got something in there. We don't have to throw away the other data. You know, we talked about it when I was here last time about how if you just delete rows where you have some data that's missing, you lose all the other data. So we have a row with 32 attributes and we're missing an age, and then we throw out all the 31 attributes that are there. So we lose a lot of value. And the age is not going to be a big deal because it's so correlated anyway with their graduation year that it doesn't matter. So we could even just ignore the age column probably and not really change much of anything. So the other thing that we want to do is we want to standardize the data. In this case, we're going to use a Z-score standardization. This is what the author used in his research. The reason being that it puts everything on the same scale, but it gives us a relative frequency. So if the number's positive, then it's above average for that column, and if it's negative, then it's below average for that column. So it adds a little information to it as we're looking at this. So there's a function called scale that's built into R that we can use to do this. So we're going to, if I can find where I'm at here. So we're going to actually create a new data frame called interests, and we're just going to take out the data, all of those keywords, and because we don't want age and gender and that stuff that's up front. We just want those interests. So that's going to be teens, and it's going to be column 5 to 40. So now we have our we have interests here, and we can see it's just all those values, all those keywords. So we have 36 total variables now. It's just those interests. So we also then want to use interests, and let's create a new data frame called interest underscore Z that's going to hold our standardized results. And so we're going to have to save that as data.frame. And we're going to use the lapply function again inside that. And then what do we want to apply? We want to apply to the data frame interests, comma, the function scale. So that lapply is like an inline apply where we just say, here's the data and here's the function we want to apply, and it's going to apply it to all the data. So think about it, for those of you that have written programming code, there's looping and pulling out individual values and changing them and saving them back. All that's built into all of this with these vectorized functions. So let me run that, and I'm in good shape. So let's look at the summary for the word basketball, the term basketball in the original data. We have a max of 24, min and mean of 0.26. So there's not a lot of people that have basketball, but some have it a lot. And then we look at the Z-score version, and you'll see that the min, median, and first quarter are all minus 0.3322. So they're all below the overall mean, which is going to be 0 because it's a Z-score. The Z-score is a statistical tool where you can convert everything to the same scale, where it's all basically within +3 or -3 standard deviations of the mean, and the mean is 0. So that's kind of a separate thing we're not really talking about here, but it gives us it puts everything on a similar scale, but also lets us know with a negative number that it's below the mean for the overall. So like I said, just adds a little extra info. We could also put it all on the 0 to 1 scale if we wanted to. Z-score is just another way of standardizing. So now with that interest Z, we can run a model on that. I mentioned before that we could run different random number generator stuff and wind up with different numbers because we have different versions of R. This is how we can take care of that, is this RNG version, random number generator version, by specifying a specific version like I do here. Then now when I set the seed and run any random stuff, we should all get exactly the same values. Again, we get a warning about something used in there just to be aware of. And I'm going to set the seed to 2, 3, 4, 5. It doesn't matter, as long as we use the same one, we'll get the same results. But then this is actually going to be anticlimactic here. I'm going to create an object called team clusters, and I'm going to use the k-means function to do that, and I'm going to do it on interests underscore Z, and with k equals 5. And that's all we need to run a k-means model, is the data and how many, we've got the data prepared, and then how many, what our value of k is, how many clusters we want to look at. But let's take a look at some of those results. So let's look at the size of those clusters. It's on, just real quick here. Some of the stuff, we have a vector of cluster assignments. So that's which cluster was the data point assigned to, and then what are the coordinates for the centers, and then what are the size of the clusters. That's all in the output. So if we look at team clusters size, you'll see there are 5 clusters here like we were expecting. And there's the size of each one. So the second cluster has 600 data rows in it. The fifth one has 21,514. We can also look at where are the, what do the centers look like? Team clusters, $ centers. So let me back up, and it shows you. So cluster 1 has the center is at, for basketball, it's at 0.16. For football, it's at 0.23. Cluster 5 has negatives for those. So, and then cluster 3. So it looks like cluster 3 on both of these are the people that talk about basketball and football the most. And cluster 5 is probably the ones that talk the least. So that's how we can use that to take a look at some of the patterns that are in the clusters to be able to apply it. So we could give it some kind of cluster names. And in fact, I didn't incorporate it in this example, but the author of the book, I said that sometimes we use domain name or domain knowledge or something else to come up with a number of clusters. The number of 5 for the number of clusters is based on the movie The Breakfast Club. That's what the author based it on, because there were basically 5 high school student stereotypes there, the jock and the cheerleader and all that kind of stuff. And so they did it with 5 and let that run. Like I said, it could be business rules or something else that determines how you're going to pick your K value. But that is one of the, that was how it was picked in this instance.
Is there a way that we can see just one of the cluster's centers at a time?
like all of the centers for cluster 1?
Right.
Or,
Because just the naive bracket 1 just gave me like the first one for basketball there.
okay. I have not looked at that. Because one of the things that I like to do is this next step of assigning the cluster numbers back to the data. Let's see. I'm sure there is a way. I mean, it's just the result. Team clusters is a list, but it's a specialized. You see, if we click on it, it's a specialized data frame because it's or data structure because it's the output from that function. So we can get some of this data. We can get cluster and centers and size, and we can also get this if you want within sum of squares and all that. But cluster, let's see, centers. I don't know how to specifically do that, but there's got to be a way to get it out of there.
Okay.
But here, if I apply those clusters to the original data frame, they're going to share indices, so they're going to line up. So now if I look back at the first 5 records, you see that those first 5, here's the clusters that they were assigned to. And then we can look at some of the other characteristics of the different results. So we can look at the mean age by cluster. And there's really not a whole lot of difference there, which we wouldn't really expect to. What about the proportion of females by cluster? There's a little difference, but again, not a ton of difference. But I think our group was more females than males anyway. So our lowest one is 70% female, highest one about 84% female, a couple of them. So not a whole lot of variation there either. And then number of friends by cluster, there's a little more variation here, maybe 28 versus 41. So apparently cluster 1 is a little more sociable. I don't know how you want to do it, but it's the thing with the clustering results is that you have to go through it and play with it for a while and see if you can, it will identify patterns, but then you as the analyst have to decide if those patterns are meaningful and if there's a label you can stick on them. So if you know that, if you look at a cluster and it looks like, oh, that's all the sportos, then maybe that becomes your cluster. Or like if you're talking about a company selling technology stuff, you can identify who are the first adopters and who are the people that lag behind and who are the ones that that buy on price. And there's a lot of different clusters that you can look at, but it takes a little work to go in manually to figure out what each of those clusters mean. I have some more code here. I'm not going to run it, but I'll let you do because it earlier one of the reasons I was sweeping out the stuff in my memory was because the last one wasn't working very well. It was because it runs for a while. But I mentioned before that I would talk to you about how to find K if you don't have some other reason that overrides it, like a business reason or whatever. If you just want to look at getting the different values of K, what you can do is experiment. Run the model with a bunch of different values of K and then compare the versions, the results, and see if there's a big change in the way it comes up with results. And we can plot the sum of squares, and it's the elbow method that was mentioned in the slides. If we plot the line, and depending on how we do it, if it comes down and then it bends really quickly, that bend then is the best way the best K value to pick, or something around there. It could be flipped and it could bend down. It just depends on how you do your axes. So what we do is just loop through with different values of K and create the model and then plot it. So I've got the code here that does that. So you'll see it creates this range variable and then it goes in here and runs this loop. And so we'll see that actually every time we run it, we'll get slightly different results, but that's going to plot here. Yeah, and this is already running slow enough. I definitely don't want to run my last one. It's going to tie it up for a while. But I'll show you. So this is the plot. Now you see there's no elbow there. So with this data, the elbow method doesn't do us a whole lot of good, but we will a lot of times see the data come down a little steeper and then turn at some point. So you've got different K values here, and this is the within sum of squares. And when the within sum of squares doesn't fall very much anymore, that's where we look at our K value. So you could maybe make an argument that here at, I guess it's probably 16, 17, 18, 19, yeah, so 16, maybe that's a good one. So you could try that. But there's no real definitive, you could even try 10, no definitive K value here. So one of the things, and if you run it again, you'll see it'll change just a little bit because of the random variation. So really the way to do this and get an accurate result is to run each version a number of times. So in this case, it runs 1,000 times and keep all of those results and then plot that. So you see there's a little bit of code here. We've got this for, we use the curly braces and all that. So it has a loop within a loop, and you're welcome to mess with that. You can change, instead of 2 to 20, you can change the values there. Instead of 1,000 times, you can make it do 100, or 1,000 and 10,000 are kind of standard values that people use on stuff like this, because doing it more usually doesn't add any value. So you can do this and it'll give you another plot. And like I said, this had my computer tied up last time I ran it for several minutes, so I'm not going to run it now. But it doesn't give you much better. It doesn't really give you an elbow that way either. But there are some data sets where you definitely see a fall off. So it all comes back to judgment, basically, and experience. So that was what I had for today. I don't know if anybody had any questions or anything for me, or like I said, this is stuff that I do in a whole semester. And one of the things with I think pandas and Python are a little more user-friendly. R is really powerful. As you saw, we could do a lot of stuff with 1 or 2 commands, but it does have a steep learning curve. And it does take a little effort to learn it. And every time I go back, I have to kind of refresh on some of the stuff. I don't use it every day, but it's in some disciplines or companies or groups or project teams or whatever, one tool might be preferred over the other, and it just takes some practice to learn about it.
That's what I was going to ask, Mike, is if you're getting comfortable enough with both that you have developed a preference. That was question 1, and then question 2 is, what can R do that Python cannot? You hear that argument occasionally.
I really don't think that there's anything that it can do that Python can't at this point. They've been converging. If there's a function in one that people that use the other like, then somebody will write the package to do that. And especially the mainline stuff. I mean, you can do k-means and k, all the stuff we've done today, you can do easily in Python too. I do structural equation modeling and some research stuff that I just did, and I'm doing that in R. I don't know that there's an SEM for Python, but I haven't really looked either. But so if you get into some really advanced esoteric stuff, that it can be a little bit different, but there's all the text mining and other tools there. I prefer pandas, quite frankly, but I do the SEM in R because that's where I do it. But I'm starting to do it in the notebook now.
Mhm.
I like the notebook so much. But R Studio is still great. It's got lots of great functionality in there, and it is kind of the standard for using R still.
Yeah, I got everybody set up. Everybody in the class can do R or Python in the notebook. You set up an environment where you can just
Yeah.
pick your language, and works pretty well.
Yeah, the problem I ran into it, I was on doing this rewrite on this paper that we just turned back in. I had to rerun some analyses in this SEM analysis, and the package that I was using, you can only get an older version of the package that works in the notebook because it goes through Anaconda to work in the notebook, and to use the newest version, I had to do it in RStudio. So there are some some trade-offs, but most people don't use that kind of stuff. So
yeah. Well, we didn't go into the Spider IDE, but I'm glad it was fortunate that both Whitney and you showed people showed us what these IDEs can do versus the notebook. There's
the Spider IDE. I don't know if you've played with it at all. It's just basically like a typical basic programming IDE. I mean, it's a screen. It's got the color coding for different words, terms, and stuff. It's got some tools built into it, but to me, I'd much rather use the notebook.
There you go, guys. Any questions for Dr. Ellis? This is our last session of content before you guys finish up your individual final projects. Either about this R or Python or Jupyter Notebook or the meaning of life or
I'm jealous. I'm jealous about the projects coming up. The little bit you told me about.
I'm really looking forward to it. 2 weeks from today, we'll come back together and do just a final brief presentation using the the data analytics life cycle of acquisition and cleansing and model building and results, communicating results, that whole cycle. Okay, well, it doesn't sound like anybody has any questions. Guys,
this is Scott. I just have one comment. So going through this and going through some of the Python workshops that we've done, I think that for me, R feels like it's more complex than Python and Pandas. And being someone who's really getting into both of those, what I'm probably going to find myself doing more is focusing on one. And then once I get proficient at one, probably Python first, then get into R down the road. But I think that if I try to handle both at once, I'm probably going to confuse myself.
That's a great strategy. I had a grad student last spring who was doing data mining with me in R on Monday night and Python on Wednesday night. And we almost had to have him committed by the end of the semester. So, it's just even those little things like pd.read_CSV versus read.csv in R. It's so frustrating because you really have to get good with one before you try to do the other one. And you can translate it, but like I said, and that Scott, that you've seen, is that R has a steeper learning curve. But man, you can do some powerful stuff in it. So that's they both have their place. So that's definitely a good strategy to use.
Yeah, it seems like
kind of what I'm doing too. Is I'm trying to get a lot deeper into Python, and then I can because we've talked about, well, let's just do everything in R or everything in Python, or but we're not. We're still trying to give everybody a taste.
It seemed like the data frame syntax and was a little more straightforward in R. It seemed like, but I'm going to continue learning Python because it's more broadly applicable. R is really only for data science, but you're starting to see Python in like full stack web stacks. So it not so much mobile, but it's just more broadly applicable. And I took the trouble to get up at least crawling, walking with it. I'm not going back and learning yet another language.
Right.
You
Well, and
know.
R was created by statisticians. So
Yeah,
that kind of tells you everything you need to know right there.
I'm
So,
decidedly not a mathematician. Yeah.
yeah, so it's really for statistics, and that's where I first ran into it. Was people were using it for just statistical analyses. I mean, just looking at getting mean, median, and mode, and that kind of stuff, and then moving on from there. But yeah, you can do ANOVAs, and there's all kinds of tools or stuff to do that stuff really, really simply once you can get over the hump on learning some of the syntax and stuff.
Okay. Well, I will conclude with my contention that the real power of code isn't so much in the interactive mode like we've been doing it. We've been, code a little, see what it does, code a little,
Right.
see what it does. It's really in automating something that's arduous and error prone, and something that you do every week for 45 minutes. I take this file and I do the same steps and glue this stuff together and then pass it on. If there's anything like that, that's repetition, that the rules can be written into code, you're always going to be better off writing a program to automate that.
Yeah. And there's plenty of stuff you can do, and you can do that with Python. You can't do it as much with R. I've done some stuff. I take a lot of pictures when I travel. I got a couple on the wall behind me, but they always come out. They're very big, and so I wrote some very basic code in Python that'll save smaller versions that I can use other places. I also wrote a deal to add a colored box on the picture with the location and the date, and change it so I could add a code in there to whether it would be dark on light or light on dark, and which corner it would be in, and I've made a collage and stuff, and done this for my wife to make something, but fiddling around with stuff like that. And I had problems with, I had a bunch of music in iTunes that I bought over the years that still had digital rights management stuff on it, because I just never got around to converting it. And so I wrote some Python code to find out where those files were, so I'd know. I had 400 and some odd tunes, so I was able to fix all that. But I had to find them first, and going down all those trees for files and folders and stuff, and figuring out where it was the first step to going in and trying to fix all that stuff. And I just recently have gotten to where I can get data off of Yahoo Finance for a project that we're doing here. And that's one of those, I just need to give it a list of the stock ticker symbols and let it run, and gather that. And then I've got some other code to clean it up. So to your earlier point, Don, is like, it took a while to work it all out, but now I can just hit a couple of buttons and get it whenever I need it. So, and I could change the stock and stock tickers and all that. So that's stuff that you can actually do it in R, but I think it's a little easier in Python. Like I said, each one's been expanding to they've been kind of converging. So, but it's easier in Python, I think.
That's where I'm headed.
Can I just really quickly, a little bit of a commercial for us? I don't know if you guys are aware. We are, I'm not necessarily talking about any of you guys, but maybe somebody or your companies should keep an eye. We have, going through the process right now, a Master of Science in Applied Data Analytics degree. We expect it to be in place, get approved and everything, because it's got to go all the way up. The governor's mom has to say it's okay. I mean, it's like it goes through everybody. And then that should be approved by this spring and in place next fall. So we've got a graduate certificate in data analytics now that's a 4-class program, but we have several students that are waiting for the MS program to go live next fall. So we can go in, and hopefully we're going to get a data mining 2 and some other stuff as we go into text mining and other things. So we're expanding our options there, because companies and the governor and the president of the university have been pushing for us to do stuff like this. They do it over in what is it, math, that has a data science. I think it's math or stats. But that's really the nuts and bolts behind the scenes, statistical modeling, all that stuff. We're talking about a more applied thing, kind of like what you guys have been doing, but on a little larger scale. So it's going to be out there. So keep your eyes on the news, and hopefully we'll have that going next year.
What
All
is
right.
you said there was a certificate in place already?
Yeah, it's a 4-class. It's 2 classes are required. The data mining class that I do in R, and our business intelligence class where we do a lot of Tableau, and then talk more of the management side and the general side. And then you can take two electives in there. We have a data management class that does SQL and some data warehousing stuff, and we have a prescriptive analytics class that does some, what does that use? I don't remember what some of the other classes use, but we've got some other options in there. We're trying to get a simulation class going. We're just trying to see who's going to do it. So there's some other options, and it's just a certificate, a 4-class certificate. And then if you do this, the students that do the certificate, they can apply those classes toward the MS if they want to stick around. We have an MBA concentration in information technology, but that's not useful for you guys. If you're doing this kind of stuff, that's not at all useful.
Is do you teach the data mining class?
I teach the data mining class, yeah.
And is it kind of expanded semester long version of this lecture?
Well, I don't take this lecture and expand it into 16 weeks, but it's similar. It's similar to that.
Well,
I'm going to assume you didn't actually
vice
mean
versa
that way, yeah. But yeah, we do some other techniques and go more into the, like I said, a fool with a tool is still a fool. So go more into the background of all these things, the stuff I blew through in the slides, and more of an analysis. And we hopefully going to do a group project at some point. That's another thing with the MS, is going to have a capstone project course. And we're going to hopefully be able to work with some companies at some point to work on some real data. And so all of this is all gearing up now. So as soon as Governor Hutchinson's grandma says it's okay, then we'll get it. It's got to go through the Department of Education and everything. But yeah, we do it in R, and of course we start by covering R because most of the time nobody has seen R at that point when they come into that class, because we're not using it anywhere else in the College of Business. So the first 3 or 4 weeks are R, and then we get into the different machine learning things.
I think the U of A up here in Fayetteville is kind of going through the same thing. I know that
they do.
There's a group here that's pushing real hard to get that in place, and I'm wondering, like, is there any crosstalk between your institutions in terms of coverage, or are you just going through the same?
No, there's lots of talk, and in fact, part of the approval process for this new degree is that it goes out to all the other schools in the area, and they comment on it. But yeah, the people are all talking at the different levels.
Allison, one of our sponsor, the Arkansas Center for Data Science, one of their missions is to bring educators together and try and get the 3 systems. There's UCA, and then the state, and then big U of A system. Try and get those 3 systems, and even within U of A, they will sometimes go off on tangents. But to get for data science, get them on the same sheet of music so that the credits are more transferable and the programs are more harmonious, for the sake of Arkansans, as opposed to, there's a lot of motivation for each individual college to, once they get their hooks in you can't transfer so that they produce more graduates. It's just the way the system is set up. So yes, the universities are being encouraged to talk to each other about these programs, especially since it's sort of a new direction for.
Yeah, and we're not trying to compete directly with Fayetteville. That's why we had long discussions, and we're doing an applied data analytics Master of Science. So we're going more on the applied side, the business user side, rather than getting into the theoretical or computer science type side.
I wasn't assuming that you would be, but I just know a little bit to be dangerous about what they're working on up here. So I was wondering if kind of.
Yeah, and in fact, I substituted for our department chair and the dean at one of the meetings down here a year or so ago, where they were talking about all this stuff with the different or groups and everything. So yeah, there's a lot of those conversations going on.
Yeah, I learned a lot at that session of the way the rules are set. The colleges are kind of bound to not cooperate on transferability and making sure that there's a one-to-one for the class, that the classes that they offer are somewhat equitable with each other, equatable. There's just a lot of and this is just higher ed politics. There's just a lot of motivation to not have people transfer. So that's
In
what
our
one
case,
thing
I
they
don't
were
know.
trying to do.
I'm sure Fayetteville is probably a little more regimented, but in our case, I mean, we sign off on stuff. If it, we'll go in and evaluate here in our department. If you've had a class somewhere else, does it look like it'll work? Yeah, we'll give you credit for it. I don't know. I don't think they're probably as flexible at the big schools, but we take a practical look. But there's just been a lot of pressure, and of course, we've seen a lot of it in the marketplace. And back when we used to do career fairs in person, we talked to a lot of employer reps and everything, and so we know that there's a need for it out there. And Fayetteville can't cover everything, cover the full spectrum. So there's definitely a place.
Okay.
So,
We're veering off topic slightly.
Yeah.
So any questions about anything that Dr. Ellis has brought to us? All right, I'm going to stop recording.
Okay.